Let's see. So let's see. So we'll do end about 10 minutes early to go over the project and potentially over the quiz. So before we start, are there any questions from last time or any general questions? Okay. So today what we're going to do is we're going to talk a little more about k-space trajectories, and then we are going to talk about sampling of k-space trajectories. All right. So these are the sort of relevant concepts and also the sections in the book that are relevant. And just to remind you, what we discovered last time was that the signal that we measure in MR, the signal S of t, is equal to the Fourier transform of our object, where in this case we're doing t imaging, so we've limited to m of x, y. And the thing that we're going to talk about today is essentially where we are in k-space is totally determined by the gradients. Okay? So, and the formula is kx of t is just gamma over 2 pi, and it's the time integral of the gradient. So whatever the integral is up to a certain point in time is where you are in k-space. Okay, and we assume we're typically for most MR experiments we always start up at the center of k-space because when we tip the magnetization, all the spins are in line at time equals 0. So we start at the center of k-space and then we move away from center of k-space. So the key is that the gradients control where we are in k-space. So just this was an example we did last time. So basically we have the RF pulse, and after the RF pulse all the spins are in phase. So at time 1 we're in phase, and so we're at the center of k-space. Then we start playing this gy gradient, and so that starts creating changes in the orientation of phases along the y direction. Okay? So at time 2, we've got a period denoted by those pink arrows. And so we're somewhere out in k-space. And then as we keep playing that gradient, we get more and more spatial variation. Okay, the spins get more and more out of phase. And so we're at time point 3, we're farther out in k-space. All right? And so each point in k-space, remember, corresponds to a spatial pattern of the spins. Then we turn off the gy gradient, so we're not going to accumulate any more phase variation in the y direction. We're going to keep what we had accumulated. I'm going to turn on the gx gradient at this point. And so this is going to add spatial variation in the x direction. So combined with the spatial variation we already had in the y direction, we have variation in the x, the y, and the x, so that gives us a diagonal variation. And that's shown in this plot here. Okay? So now we're out at this diagonal point in k-space. So that's the basic picture you should have in mind as we're moving through k-space. So the example we did was a fairly simple example, and we're just going to augment it today. So oftentimes you might be asked to, for example, draw as a function of time where you are in k-space, kx of t. Okay? So in this case, it's simply we're integrating that gradient over time. So it would just be a simple linear function. Okay, so we're just moving out in case along. And now notice this is the kx of t, and the y-axis is t now, as a function of time. All right, so that's one way we might draw where you are in k-space. So we'll talk about different ways we might draw where you are in k-space. The other way we draw it is a parametric equation where we have kx and ky on the axes, and now time is the implicit parameter. So that would be more of a parametric graph. All right, so we'll look at both examples in a minute. So then to do the computations, you simply take gamma over 2 pi, which in this case we're saying is 4257 hertz per Gauss, and we just multiply by the area. So at this point, this area is just the height here, which is 1 Gauss per centimeter, multiplied by this time. So that at the end, we're at this point in k-space. Okay? So at this time, 0.2, what is it? 235 milliseconds, we are at 1 inverse centimeter. Okay, so that's how you might plot out where you are in k-space along just the kx axis. Okay, so let's say we have a more complicated trajectory. So there's two ways we can draw it. One, as we said, is a parametric plot. So here we have kx and ky along the two axes. And as a function of time, we're moving out along the kx axis first and then along the ky axis. Okay, so that's one way you want to think about it. And that's typically when we think about going through k-space, we want to think about traversing that space. But that can be sometimes hard to think about. So it's also useful to plot each kx, ky individually as a function of time. All right, so let's do that here. So as a function of time, say we have here time. Let's do kx and ky. So this is kx and ky. These are both a function of time. All right. So initially, there's nothing happening in ky up to this point in time, so it just stays 0, right? And the kx axis is increasing linearly, okay? And then when I turn it off, it just keeps that value, right? It doesn't change anymore, right? And then the ky axis starts increasing linearly here, okay? And if we were to keep going and we turned it off, it would just keep that point in time. All right, so that's plotting each one as a function of time. And then the one on the right is the parametric plot where you're plotting kx and ky and time is the implicit parameter. All right, so it's important to keep in mind that those are the two main ways we're going to be plotting the k-space trajectory. Okay, so are there questions? Okay. So good, because now you get to do an exercise. So this is problem 3.11 in the book. This is part of your homework problem number 1. So we're going to do part of the problem for you, and then you have to just sort of fill in the details for the homework problem. Okay? So the questions you're supposed to ask are, well, this is actually augmenting it. So, so this is sort of not in the homework problem, but this will get us started. So for on the poll everywhere, I'm going to open up the poll. And once again, feel free to talk with your colleagues. And there's 2 questions to answer. Question A, what are kx and ky at 4 milliseconds? So 4 milliseconds would be here. Okay? And what are kx and ky at 2 milliseconds? Okay? And then after we do that, we're going to draw the plots together. All right? So just talk about that for a few minutes and then submit your answers. I'll open up the poll. You have a question? I can't. You have to speak up really loud. Just submit it again. As long as you put your names by it, I'll see who did it. That's fine. Just put your name by each one. Yeah. Okay, let's take a look at this then. So, so problem A, what is the net area of gradient of this net area at 4 milliseconds? 0, right? So therefore, we must be at kx equals 0, and similarly, we must be at ky equals 0. All right, so everyone should have gotten that. So that basically has a zero moment of 0, okay? 0th order moment of 0. So now let's look at the next one, which is at 2 milliseconds. So we want to look at this point in time. Where are we in k space? So essentially, we just want gamma over 2 pi times the area. Okay. So we have 4258 times 10 Gauss per centimeter. So this is in Hertz per Gauss, Gauss per centimeters. And then we have 2 times 10 to the minus 3 seconds. Okay, so that should all divide out to give inverse centimeters. And I believe the answer is it 85.16 inverse centimeters? Everyone got that? Okay. Does anyone disagree with that answer? Okay. So, and then for the ky, so this is where kx is. Ky is just going to be half of that, right? Because it's half the area. But you could write it out if you wanted to. So ky would just be 42.58 inverse centimeters. Right? Does that work out? Let's see. So let's just check that. So that's 4258 times 10 to the minus 2, is that right? Yeah, so 4258. Okay, so that's where we are. So that's a very, this should be, if you see this on a quiz, you should be done with this in like 30 seconds, right? So you want to whip these ones out so you have time for the harder questions, okay? So now let's actually draw the k-space trajectories. So what we're going to do is first we're going to draw it as a kx as a function of time and ky as a function of time. All right, so let's draw it out here. So kx is a function of time. So this is 1, 2, 3, and 4. Okay? So what is it going to look like from 0 to 2? It's going to increase how? Linearly, right? So all you would have to do is draw it this way. And you know it's going to go to 85.16, right? And then what happens from time t of 2 to time t of 4? It's going to decrease back to 0, right? Okay? So that's what that would look like. Whoops. Same thing for ky, but it's going to look slightly different, right? Okay, so what is it going to look like from time 0 to 1? What's the integral of a line going up? Quadratic, right? Yay, all right. Your calculus teachers would be proud. Okay. All right, now what happens from time 1 to 2? What's the integral of a line that's going down? Anyone? It's going down. So what's the integral of a line going this way? It's an unhappy quadratic, right? Okay. It's unhappy, right? It's facing down, right? Unhappy, right? Okay. Okay, remember this is happy and this is sad, okay? All right. And this point here, yeah, I know it's silly, but it helps you remember. See, I've remembered that for how many years, okay? So, so it goes to 42.58, right, at the peak. And then it just reverses itself, right? So it must go, let's see, so it's going, now it's negative, right? So you're incrementing in a negative area, so it must be going like this, right? And then it's going like this. Okay? So that's what it's going to do, and that is the sort of, if you're plotting each one separately on its own. All right, everyone okay with that? So it's basically just integrating, all right, which hopefully everyone can do. And the most we're going to do is integrate either rectangles or lines. So that's all you need to really know for this course, all right? In general, obviously, we can integrate much more complicated things, but for this course, that's all you need. And then let's think about, now drawing it along kx and ky is a little more complicated. We know we're going to go out to 85.16, and we know we're going to go out to 42.58, right? So we know that this is the point. We're going to go out to that point, and we're going to come back to 0, okay? So the contention is it's going to sort of go out like, it's probably going to go this way, and it's going to come back along the same path. All right? So that's if you took those two kx and ky and think about the parametric plot, how you do that. So that's, I've done the general form of the homework for you. Your job on the homework is to put in actual analytic equations for all those curves. Okay? So each of those sections, there should be a curve. So this has a equational, this has an analytical expression, this has an analytical expression. Obviously, they're going to have to be piecewise, right? You have to say between this time and this time, this is the equation. Between this time and this time, this is the equation. And similarly, this will have an analytic expression. Question? Why it looks like that? Okay. So basically, if you think about so kx is sort of like a function, kx is a linear function of time, right? So we know that ky as a function of kx is going to look like ky as a function of time, right? So therefore we can draw it like that, right? So we know that going out it goes like that. Now going out, coming back, kx is negatively related to time. So we know as a function of kx is going to bring us back this way. Okay, so you have to think about it a little bit, but that's for the first part, the reason I know it has that shape is because kx and time are linearly related, right? So any dependence that ky has a function of time, I know that ky will also have a similar dependence on kx. And then then you have to think about what happens when it's coming back. Okay, question?
Is that when t equals 2 milliseconds?
You mean the last plot?
Yeah.
Yeah, so here, like I started at time 0, here's time 2, and then here I'm back at time 4. Yeah. Okay, so it's just basically drawing those two plots on the left in a parametric form, which hopefully everyone has seen before. All right? Okay, so that is for your homework, problem 1. So your job is just to give analytical expressions for all those sections. For the problem 2, I'm not really going to go through it too much, but just point out some things to keep in mind, which is that, first of all, you know, when you go shopping for magnets, it's like shopping for a car or a computer. You're always looking for power and speed, okay? So these are actually from a GE system, the specs. So when we talk about magnets, we're always saying, okay, it's 5200 or it's 200-200. So these are the two numbers that get thrown about all the time. And so right now, like our system's a 5200. We're looking at maybe going to 150-200. And so that's how MR physicists talk to each other, like, how big is your magnet, right? How fast is your magnet, right? So that's like 70, 50, 200 or something like that, okay? So in this case, this has a maximum gradient of 50 millitesla per meter, and the maximum slew rate is 200 Tesla per meters per second, okay? So that slew rate is just how fast can you go, okay? So that means that if I were going to go from 0 to G max, okay, and I'm assuming some linear slew, okay, so I'm going to go up to G max, then the slew rate, so I go in some rise time delta t, the slew rate is simply going to be G max over delta t. Okay, that's all it is. So that's the fastest I can go from 0 to G max is the slew rate. All right. So basically, given G max and S, you can figure out delta t. And then in this problem, you simply have to look at areas of trapezoids, or in the degenerate case, when a trapezoid has 0 width at the top, it becomes a triangle. Okay? So you're basically saying, do I need a triangle or do I need a trapezoid? And so this is like one of your first design problems here. Is just, and this is actually a calculation that is going on right now in thousands of MR machines as we speak. This calculation is going on. All right? Any questions? Okay. Okay, so now what we're going to do is we're going to build up the most common pulse sequence, which is called the spin warp pulse sequence. So if you are scanned on an MRI scanner, most likely you'll have some version of this spin warp pulse sequence being applied to you. There's lots of variations, but this is the most basic form. So the basic building block of the spin warp pulse sequence, and spin warp pulse sequence is just one way of getting through k-space. It's one of the simplest ways of getting in k-space, which is why we introduced it first. We'll talk about some more complicated ways in a little bit, but for this class, we're really going to focus mostly on the spin warp. So this is the basic building blocks. The Gx gradient always looks the same. Okay, it just gets repeated over and over again, and we'll explain why. And the Gy gradient, we're going to vary its amplitude over time. So we're going to do lots and repetitions of this spin warp pulse sequence. Each time we do a repetition, we're getting one line of k-space. Okay? So let's see what this basic building block does. So let's say we're going from time 0 to t sub 1. Okay, so we start off here at 0, and at time t1, those gradients move us out to some place in the lower left-hand quadrant of k-space, okay? Because they're both negative gradients, so they're going to move us out to there. So it moves us, those two gradients at the beginning, that's our starting point. All right, that like moves us out to our initial place in k-space we want to begin. And so let's say this is time t sub 2, then from t1 to t sub 2, the Gy gradient is turned off, so we're not going to move any more up and down in k sub y space. We have a rectangular gradient in G sub x, so we're just going to linearly move across k-space. All right, so that's what this line is. So this is a linear traversal in time of k-space. Right? So that's the basic building block. So the way we do a spin-warp pulse sequence is we acquire k-space over many, many repetitions of this pulse sequence. Each repetition starts off with an RF pulse, which excites the magnetization. Okay, we've talked about RF pulses a little bit. We'll talk about it some more probably on Wednesday. And for now, just assume that all the spins are aligned after every RF pulse. So after every RF pulse, at this point in time, we're at k equals 0. Okay? So we're at the center of k-space, right after the RF pulse. Okay, so kx equals 0, ky equals 0. We're at the center of k-space. So then the gradients come along and they move us away from the center of k-space in a way that we want them to move us. So for example, this first set of gradients moves us out to some initial point here. Let's see, get a different color here. So we're out to here in k-space. Okay, so that cyan gradient moves us out to there in k-space, and then the readout gradient. So this is what's called the readout gradient. And the reason it's called the readout gradient is because as we're going along k-space, we're reading out the data as we go through k-space. All right. So that's the first line of k-space. Then we let the spins. Typically, we want the spins, the transverse magnetization to die away, some regrowth of the longitudinal magnetization, and then we excite the spins again. And then we acquire another line in k-space, okay, which is not as far out in the ky direction because this amplitude now is smaller, so we don't move as far down. All right. And in the last repetition, the gy gradient has an amplitude of 0, so we're basically just staying at ky equals 0, moving out, and then zooming back. All right. So that's how we cover k-space. In general, we're going to have gradients that are both negative and positive. So these would be negative gradients, these would be positive gradients. Okay. And so this one gives us this, and this one gives us that. Okay? Question?
So as you go through all these gradients, are you essentially trying to cover every single y position so you kind of get the entire x-axis of k-space at a given y and just kind of try to go through all those y's?
Yeah, so we'll talk about that. So basically, k-space is the Fourier domain, right? So we're going to, the second half of this lecture is talking about how much of k-space do we need to get, how finally do we need to sample it. Okay? Because obviously, if we go out to infinity and have infinite resolution, it'll take an infinite amount of time, so we can't do that. Question?
I have a question about dy of t. So is the amplitude always reducing as we move forward, I guess? Or
Yeah, so in this case, the order actually is up to you. But by convention, you know, it's easier to think about, start off with a negative gradient, and then it reduces, and then it becomes more positive. But in practice, actually, sometimes it's advantageous to do different orders. Okay. So to present it, we're just assuming we're going to go through like this. But in general, there are advantages. Sometimes there's advantages to going other orders. Question?
Yeah. So does this mean that the criteria associated with reaching a particular k-space value is only dependent on the amplitude and not the time? So
No, that's a good point. So this time, let's call it t, is just the same each rep, just to keep things simple.
Just going on that, is it easier, or sorry, is it from an operation point of view, is it better to have a lower amplitude and a longer time, or a higher amplitude and shorter time?
It depends. If you are going as fast as possible, then you want to have maximum amplitude. Now, in this case, if you're doing repeats, if you change the timing, then it can change some sort of system characteristics that can introduce artifacts. So in that case, you just want to keep the timing the same between repeats and vary the amplitude. And there's other aspects we'll get into. But so the answer is it depends.
So
Yeah.
technically, you can do both.
You can do both. Yeah, you're always at the end of the day, you're always trying to optimize performance, and so what performance means can vary depending on the application. Yeah. Was there another question? Yeah. Oh, okay. So that's a good question. So basically, you could, right? But in general, the simplest thing is you just want lines in k-space, right? So, I mean, you could use that data and read it out as you're going. But typically, as alluded to the previous question, we're going to try to make these gradients go as fast as possible. We're just going to go zoom right in k-space. So we're not going to have much time to read out the data there. And then we'll take our time going across the line. But you could collect the data there, but then it makes your life more complicated later. Okay, question?
So in the second dark blue pulse,
Mm-hmm.
are you not going as down as in the light blue one because the amplitude of the GOY has been reduced?
Yes, that's right. The amplitude is reduced, so we're not accumulating as much negative area. Right, the area is less. Yeah. All right, good. Any questions? More? Okay. All right, so I'm going to show you an example of sort of a simulated MR acquisition. So assume our object is a rect function like this one. So we know that the 2D Fourier transform of that is going to be a 2D sinc function. All right. So what we would expect to do is, as we're collecting the data, every line in k-space is just one line through this. Okay, so we're rastering through that Fourier transform. So what this movie is going to show is this is the object. You're going to see here, it's going to be faint, but it's going to show in an image sort of the data as it's being collected. And then this is going to be showing sort of the profile of that line of data. So we'll play this movie twice so you can look through it. So see how it's just filling up k-space line by line by line? Okay. And so at the end, we have this two-dimensional sinc function. So that's basically what a basic MR acquisition would look like if you're looking at the data that's coming in. It's just filling in line by line by line. So we'll play it once again. Okay, so that's basically, so if we had an oscilloscope and we had a square object, we'd actually see sinc functions coming in on the receiver channel. All right. So as I alluded to before, there's lots of ways of going through k-space, and let me just see if this works. And so what we've talked about is what's sort of Cartesian, which is the simplest thing of just going line by line by line. But there are things like spirals. So for example, the square spiral acquisition was done by a graduate student maybe 30 years ago. So that's already been done. But there are now sort of Archimedean spirals that are done. There's zigzag and there's a radial. These are very common ones. So what does the radial acquisition remind you of? CT, right? So the nice thing is you can actually make MR look like a CT, and you could actually acquire the data and do back projection on the data if you wanted to. Okay. And there's more discussion of trajectories at that website. One of the more common ones that we use a lot for functional MRI, which is a little different from spin warp. So spin warp, remember I said, we apply an RF pulse, we get one line of k-space, and then we wait and we apply another RF pulse and get another line of k-space. So that's going to take a long time. Sometimes we don't want to wait, and so in this case, this is what's called single shot imaging. So we're going to apply one RF pulse and just like zigzag through k-space. Okay, so that's done with these gradients here. So here's the RF pulse, and immediately after that, we apply these gradients that basically cause us to zigzag through k-space. Okay, so for the homework, that's going to be assigned. This Wednesday, you're going to have an example of an EPI gradient wave trajectory, and so that's just pointing out that that's what that's doing. So your answer should be a zigzagging through k-space. All right. I'm going to play this. I'm not sure how if the sound's going to pipe through here or not, but let's just give this a try. Oh, that's not good. Let's see. Volume, muted, microphone. Yeah, so anyways, I'll walk you through this, and I'll put the video on the canvas so you can listen to it. This is essentially, so he's saying he's at Children's Hospital in Cincinnati. And they study disorders of kids with throat disorders. And so they're going to look at the function of the brain as kids are swallowing. And so this is what a pulse sequence looks like. This is sort of, and what they did here is they basically put a sound file of bagpipes playing into this. And so the gradients are actually just a digitized, so that's what the gradient waveform looks like. So he's putting that gradient waveform into the MRI machine. And the MRI machine, as we said, is like a big loudspeaker. And so what happens is if you're sitting in the MRI scanner, it just sounds like bagpipes playing. Okay, and then what you can do actually is you can let's see. So that's where they're showing the bagpipes playing, and then what they did for this one is they basically also made the MRI machine talk to the subject because they're kids, and so they had it tell them when to, like, this is like swallow. So the MRI machine would just tell you to swallow. It's actually the gradients talking to you. Okay, and so here what you're seeing is the RF pulse sequence playing. So that's actually an EPI waveform being played out there, and then they're swallowing, and then they're just repeating that over and over again. Okay, so those up and down, this top row there is actually like these gradients here. Okay, so I'll put the video online so you can hear the sound. There's this setup it's hard to get sound through it. Okay. All right, any questions before we move on to sampling? Okay, so now for us to figure out the last part, sort of to design, we've talked a little bit about designing gradient trajectories to get you a certain part and case space. And so your homework problems are giving you some taste of what that design process looks like. The next step we're going to talk about is sampling in case space, which you've already had a little bit of a taste of this in the Fourier Transform MATLAB exercise that you had in a previous homework. So the basic idea is in MRI, we're sampling in case space, right? Because we're acquiring the data in case space, and we're deciding how much data do I need to have a good image, okay? So for example, this is my image, and this is its Fourier transform, right? And then I inverse transform it, then I get a pretty good image. But in this case here, and this is what you did in your homework, if I skip every other line, let's just say I don't need all that case space, I'm just going to take every other line of case space, then what you saw is you get this effect, where the image is overlapping on itself. Okay? So this is what's called aliasing. All right? And it's generally not desirable to have. Right? If you go to the hospital and your image comes back like this, you're not going to be very happy. Okay? You're going to say, what's wrong with my head? Do I really have 3 heads? And it's also going to make it hard for them to sort of see what's going on in the image, especially where it's overlapped. Let's say there's a tumor there that's very faint. When there's overlap, it's very difficult to see. So basically, you should never have aliasing, okay, unless you ask for it for some reason. Okay. So this is now skipping every other line in KY, and now we get repetitions in Y. And this is skipping every line in KX and KY, and now we get repetitions both this way and this way. So that's what you saw in your homework. So now we want to just review some basic concepts, work up what the design equations are to figure out how do we avoid aliasing, and also how do we get the resolution we want to get. Okay, so let's go back to that simple example we did in class where we had the people standing in line. And remember, they started off all in the same phase, and over time they got out of phase. Okay, and we said that as they're getting out of phase, each pattern of that is like a different part and case space. Okay, and so as they evolve more, they get more out of phase. And now what we're going to do is, in this case, we have, let's say, 6 people. So we only had 5 people in our example. Now we're going to expand to 6 people. So the red circles are sort of encircling 2 people, right? So these are the directions those 2 people would have turned during our experiment. All right. So what do you see? What can you say about those 2 spins? They're doing the same dance, right? So they're in different places in space, but remember when we do the MR experiment, we don't know where things are. We just integrate the spins from everywhere, right? We have no idea where it is, and wherever it is, it goes into the integral. So when it goes in the summation, those two spins go in the same exact way. Okay? So from the point of view of the experiment, I don't know whether the spin's here or here. So that's why we get aliasing, right? Because if the spin does exactly the same thing, then when it goes into all my calculations, it appears to be the same. All right? So that's aliasing. So what could we do? And similarly, these two spins here also look exactly the same. Okay? So basically, the aliasing, this spin would appear as it's here, this spin would appear if it's there. Okay? And that's basically why aliasing occurs. So what could we do to avoid aliasing?
Take one more.
Yes, go ahead.
Have your sampling be twice that.
Yeah, so take smaller steps, right? Yeah, so let's see if that works. So now we fill in those steps. And now, do those two spins look different or not? Yeah, they better, otherwise the example wouldn't work, okay? So now we can actually, the way these two spins come in to the summation is different, okay? So now, when we look at all the points in K-space, they have different, we can tell that there are different places in space, okay? And so essentially, this step here, let's say this step here was some delta K sub 1, what we said is the step actually has to be delta K sub 1 over 2, right? We have to have, our steps in K-space have to be smaller, okay? So what we're going to do is we're going to try to come up with what is our delta K? What's the design equation for delta K? Okay, another way of thinking about it is this. Imagine you have your object. So FOV stands for field of view. I think you guys went over that in CT. Okay, so field of view is essentially a parameter that you set when you're imaging. It's like, this is the biggest object I think I'm going to have. So you always set the field of view larger than the biggest object you think you're going to have. So let's say we have this object with this field of view, and it's sort of composed of a pink part and a green part. So if my smallest kx is 2 over the field of view, okay, so then the one period goes from here, let's see, to here. Okay, so that's one period there. Okay. All right. And so in that case, let's say this part of this object and this part of this object, they essentially get assigned a spin that looks the same. Okay, and similarly, let's say this part of the object and this part of the object, they also get assigned spins that are the same. So when we go to reconstruct the object, those two parts are going to lay on top of each other. Okay. So what I actually need, if my object is this big, I actually need to have something that's got a period that's just as long as my object. So this is now the period. Okay. So now this spin and these guys have different spins assigned to them. And this part also have different spin orientations assigned to them. Okay. So this actually gives us our design equation that we need our delta K to be 1 over the field of view. All right. And so the way it works in an MR system is the user will enter in field of view. The first calculation we do is delta K is just 1 over the field of view. So what could be simpler, right? Right. Okay, so now we're going to actually spend maybe 5 to 10 minutes just going over the math. And so this is more just as background. So the main thing you're responsible for today is the design equations, but this is just sort of showing you where it comes from. All right? So remember, sampling is taking some analog waveform, g of x, and coming up with some digital samples, g of n, where each sample might be g of n times delta x. So the sampling interval here is delta x. All right? The way we represent sampling is with a comb function, which is just a bunch of delta functions. And the comb function, by definition, has a spacing of 1. Okay? So the comb on its own has just a spacing of 1. All right? But obviously we want scaled comb functions, so what we actually want is something like comb of x over delta x. So now the spacing is delta x. All right? The most important thing to remember is the Fourier transform of a comb is a comb, so that's really nice. Okay? So basically, if I have a comb function, it just goes to, in Fourier space, another comb function where the spacing in kx is 1. Okay. But what we actually want is the Fourier transform of a scaled comb function. So we actually want the Fourier transform of a scaled like a x over delta x. And it turns out that gives us a comb of kx delta x, okay, by the scaling theorem. And when you go through the math, there's all these sort of leading scaling terms. I don't want you to worry about that for this class. I want you just to remember this picture. If I have in one domain a spacing of delta x of the comb function, the spacing in the other domain will simply be 1 over delta x. Okay? So if you forget, just remember the scaling theorem. If I squeeze in one domain, I have to expand the other domain. All right? So that should give you some intuition. If you're working on a problem and you get confused, this is a sanity check. The finer I sample in one domain, the more the replicas are spaced out in the other domain. Okay, so let's look at the process of Fourier sampling. So let's say this is my object. It's a rect function. Okay, this is its Fourier transform, so that's a sinc function. Right? We know rect goes to sinc. So in MR, what we're sampling is the Fourier transform. So we're going to get samples of the sinc function. So that's shown down here. And then what we want to do is we want to inverse transform that to get our image. Right? And now the question is, how much do we have to sample that sinc function to get back to the rect function? Right? So remember, the Fourier sampling is going to, so now the Fourier sampling is delta kx, right? So I'm switching notation from delta x to delta kx, because in MR we sample delta k, right? We're sampling in k space, all right? So now let's take a look at this. So this is my Fourier transform here, right, which is a sinc function. The sampling is represented by multiplication with this comb function, which has spacing delta kx. So that gives me these samples here. Okay. Now we know that by the convolution theorem, right, so this is convolution theorem, I could just take my object and convolve it with the Fourier transform, or the inverse Fourier transform of this guy. Okay, so now this has spacing of 1 over delta kx, all right, because of the scaling theorem. So what that means is whenever I sample in k space with delta k, I'm going to replicate my object with 1 over delta k. And that's where that aliasing comes from. Right? So that's what comes up with the Nyquist criterion, right? I have some object with some field of view, FOV, and I'm going to repeat it at 1 over delta k. Okay? So I need that spacing 1 over delta k to be bigger than my FOV, otherwise I'm going to have overlap. Right? So for design point of view, we just typically just set it at the limit, because typically people make the FOV a little bigger than the object, so we know we have some room. So for all your design things, you can just set delta k equal to 1 over the field of view. Okay, you don't have to worry about greater than or less than. All right. So if I don't satisfy that criteria, then the spacing between my replicas, there starts to be overlap, and that's what you saw in your homework. Right? So that's what we want to try to avoid. So this is an aliasing example here where delta kx equals 1. So we're sampling the sinc at its peak, and we're getting zeros everywhere else, right? So when our discrete sampling of the sinc function just gives us a delta function, right? And what does a delta function go to? It goes to 1, right? And so if I take, and here what I've done is I've taken my rect function and I've just spaced it by 1 apart. And if you take a bunch of rect functions and put them end to end, that just gives you 1 everywhere. Okay, so that's an example, a very sort of degenerate example of that. Okay, so moving right along in 2D, we just need a 2D comb function. So we've got things, spikes this way everywhere. And we want to scale it, so delta x, delta y. And then everything else applies. So what we're going to do in k-space now is we're going to take our Fourier transform and we're going to multiply it by a comb function which has spacing delta kx along the kx direction and delta ky along the ky direction. And so that's what this looks like here. So here what you're seeing is this is my object here. Okay, so that's a rect function. This is a sinc function. Okay, I'm multiplying it, and this spacing here is some delta k. Okay, so that's going to give me the sampled version of my 2D rect function. All right, and that's by multiplication. So here I convolve. This spacing here is 1 over delta k, and so that just takes this image and replicates it with a spacing 1 over delta k. So that's all you need to sort of remember for sampling in terms of the field of view. So field of view determines delta k. And that's summarized here, where in general you're going to be given a field of view in the x direction and the field of view in the y direction. So you're going to have a delta kx and a delta ky. You can just set these, you can just use equality for these when you're doing your design equations. All right, so just set it equal for design. Okay, any questions on that? So we'll do some examples. We'll do example right now. Okay, so this is your object. Okay, so take a few minutes, look at the equation for the object, and then tell me what is the delta kx and what is the delta ky needed to sample this object or to avoid aliasing for this object. All right, and I'll set up the poll. And don't overthink it, all right?
But you scared it. But that's why I was asking you if the divided by 3.
Okay, let's take a look at this. So there's, it's about a 50% hit rate. So we should talk about this. So let's look at this object. First of all, do I need to worry about this cosine term? No, because it doesn't determine the extent of my object. So that's just meant to mislead you, right? All right. So so all I need to worry about is this rect x of 3 and rect y of 4, right? So what does rect of x of 3 look like? How wide is it in the x direction? So rect of x is how big? It goes from minus a half to a half, right? So it says width of 1. So what is rect x of 3 equal to? How wide is that? 3, right? Okay. So this has a width of 3. So my object in x and y is going to be delimited by something that has a width of 3 and something that has a width of 4. All right. So if you get this part, then you're basically almost there, right? So now what we can say is f of v of x is equal to 3. F of v of y is equal to 4. You're told that the spatial units are centimeters, so I can say this is centimeters and this is centimeters. Okay, and then all you have to do for this one, you say delta kx equals 1 over field of view of x equals 1/3 inverse centimeters. Delta ky equals 1 over field of v of y equals 1/4 inverse centimeters. Okay? Any questions on that? Yes. Oh, the cosine? So the rect function it looks like this, right? So it's 1 here and it's 0 everywhere else, right? The cosine is everywhere, right? Cosine of 2 pi 3x plus 2y is defined at all x and y. So the rect function is what determines the limit of your object, right? Because the object only has value within where the rect function is 1. So that's going to determine your f of v. All right. Any other questions? Okay. All right, so the next thing we're going to need to talk about is, so we've talked about delta kx and delta ky. That's how finely do we sample. The next concept we need to get through today is how far out in k-space do we go. And so we're going to be trying to figure out what's the kx maximum and what's the ky maximum. Okay, because we don't want to go out too far in k-space, right? So this is what's called windowing, all right? So if the Fourier transform from minus infinity to infinity is g of kx ky, we want to multiply it by some windowing function that just only keeps the data in some window, right? That's a multiplication in the Fourier domain, so we know we're going to convolve with the inverse transform of that window in the object domain. So we want to look at the effects of that and decide what that window should look like. So this is the basic idea. This is my object here. Okay, it's a rect function. It goes to a sinc function. Okay, I multiply it here by this window. Okay, which is just a rect function that only keeps the value in this central part of k-space. So what I'm left with at the end is just the sinc function in the center part of k-space. Okay, I basically cut out all the other parts, right? So that means I have to convolve with the inverse transform of that rect function, which is just a sinc function, right? So I'm going to take that object I have, that nice sharp object I have, and I'm going to blur it out with a sinc function. So I'm going to end up with this blurry version of my image. Okay, so that's the idea, is how much blurring can you accept, and that's related to what's the resolution that you want for your image. So here's an example here. So let's say, typically we'll say the window in the x direction has some width wkx, and the window in the y direction has some width wky. So, so this would look like this. So the width here is wkx, and the width here is wky. All right. So w we stand for the width of the window. If we do the inverse transform of that, what we're going to find is our overall image at the end is the object we cared about convolved with these two-dimensional sinc functions. Okay, a sinc of wkxx and a sinc of wkyy. So two one-dimensional sinc functions, sorry. So now let's look at the effective width of a sinc function. So what we want to say is we want some measure of resolution, right? So we have the sinc function, and we want to say, well, how fat is that sinc function? So we can define the effective width as the area, so the area of the function equals its height times its width. Okay? And if you go through the math, what you find out is the effective width is just 1 over WKX. So that's nice to remember. So if I have a rect function in the Fourier domain of WKX, the effective width of the sinc function in image domain is 1 over that. So once again, easy to remember. Okay? So that's the effective width, and we're going to use that effective width as our measure of resolution. All right? Another way of thinking about effective width is imagine I have an object that's varying with some delta x. Okay? So we need to, the effective width of my imaging system had better be delta x or less if I'm going to be able to image this object, right? If this object is changing every delta x, then my effective width should be equal to that, right? So let's think about this. So if this effective width is 1 over delta WKX, then the spatial period it corresponds to is this, 2 over delta KX, 2 over WKX, okay? And that would correspond to a sinusoid that is up for half of its period and negative for half its period. So it sort of makes sense that you could represent an object that's varying every delta x with an object with that frequency, all right? So that's just another way of sort of motivating why the answer is the way it is. Another way of thinking about it is if I have two delta functions that are spaced one apart, okay, and I convolve each with a sinc function, when WKX is equal to the spacing of those two functions, 1 over WKX is equal to that, then at that point, we're right at the limit where they blur together to give you one function. The moment I move away from that, so this spacing here is 1 over WKX is equal to 1. These are now spaced 1 over 1.5, okay? So that's less than 1. So the width of those, as those width of those sinc functions decreases, then I can start differentiating these 2 points from each other. Okay? So WKX equaling the resolution is right at the limit at where you can't distinguish 2 points from each other. So we're going to use that as our resolution limit. So let's see. Let me just jump ahead. So what we're going to come up with is this, and then we'll go back to those slides. So the design equations you're responsible for this class are that if you're given the FOV, okay, then you know that delta K is equal to 1 over the field of view. All right. Similarly, if you're given the resolution, delta, then you just set the width in Fourier space equal to 1 over delta. All right. So those are the two design parameters. So you're going to, in general, you're going to have a delta Kx, a delta Ky, and you're going to have a WKX and a WKY. All right.
Sorry, excuse me.
Yes.
Can you just explain what that width in the Fourier space is again? Like, is it the whole width of the window, or?
Yeah, this whole width. This is basically. So in this case, you're going to go from minus WKX over 2 to plus WKX over 2. All right. So we're going to do one exercise on that, and then we'll also review this again on Wednesday. But let me give you this exercise here because this will help sort of have you apply this. So here's the object that you just looked at. Okay. So now the question is, what would be a reasonable choice for the resolution of this object? So you're given this object and you want to image it. And now you have to tell the scanner, I want some resolution in the x direction, some resolution in the y direction. Okay? And then, so you're given the resolutions. So you're going to pick the resolution, and then given those resolution, I want you to tell what is the maximum Kx and what is the maximum Ky parameters I need. Okay? So there's a couple small steps to get to that, but that's what I want you to think about for the next 5 minutes. Okay? So this is Kx max and Ky max. And so we'll open up the poll for that, and then we'll regroup in a few minutes.
So it is the same thing as before, right?
Yeah.
It's just a different concept. What would be a reasonable choice?
Yeah, and now we're looking
Oh, yeah.
And it's 10, right? No, that's
but it's much, it's much.
so if we're looking at the wiggles and that's now we're looking at the whole thing. It should be literally 3.
Yeah, all right, yeah. I can answer all of it. Or just one person.
Yes. So now we need to figure out what's the light position. It's just that in terms of the vector delta S,
So then you guys. It's probably not. But it's.
So for K and the field view are the inverse. So for K to be max, the field view has to be 1 minimum. It's probably not everything you should follow. And you have to use
Okay, let's take a look at this. So remember now we're talking about resolution, right? So we want to figure out, resolution is sort of like the details of the object, okay? So in that case, do we need to worry about the rect x of 3 and the rect y of 4? No, because that determines the extent of my object, right? So I can ignore that part now. Okay, that's what we had to worry about for the delta k. We had to worry about the field of view. Now we can ignore that. Okay. Now we're just going to focus on the cosine 2 pi 3x plus 2y. So let's just think about what my object would look like. So we know it's going to be delimited by some rect function, and then inside it's going to have some variation like that, right? It's a cosine 2 pi 3x plus 2y. So what we want to know is, what detail do we want to look along in the x direction and the y direction? How finally should we have basically think of sampling the image in the x and y direction, and then what does that tell us about how far do we have to go out in k-space? Right. So let's look at that. So let's just look at the x part. So we have cosine 2 pi 3x. Okay? What is the period of that function? Anyone? 1 over 3, right? Okay. So that's a function that has some period of 1 over 3, right? So what you know about sort of just sampling is what's the sort of the minimum I can get away with sampling that function? 1 over 6, right? Because if I sample 1 over 3, I'm only get the peaks. So I better sample at least the peaks and the troughs. So I know I want to have a resolution of 1 over 6. Okay, so I can say my desired resolution is 1 over 6 in the x direction. Okay. Similarly, if I have cosine 2 pi 2 sub y, what is that period? 1 over 2, right? So I would want delta y to be half of that, so I'd want it to be 1 over 4. Okay, so this is in centimeters now. Everyone okay with that? I basically have these cosines, right? And I want to sample them, right? And that's going to tell me what my desired resolution is. So now the next part is we know that we're given wkx is equal to 1 over delta x. So we know that's just going to be 6 inverse centimeters, right? And wky is equal to 1 over delta y. So that's 4 inverse centimeters. Okay? But what did the question ask us for? It asked us for kx max and ky max. Right? So what I actually want is kx max and ky max. Okay, so if the width, and I'm assuming a symmetric window, if the width goes from minus kx max to plus kx max, if my width is 6, what's kx max? Just 3, okay? And similarly that's 2. All right, so any questions on that problem? So the problem basically, so the rect part of it determines the field of view, so you get the delta k. The resolution part of that, in real life, that would depend on what you thought was in the object, right? And now I'm saying there's these cosine variations in my object, so based on what you think you want, then you need to resolve it. So for example, if you were imaging a biological object, you would have to know what's the smallest order of variation that you would care about. And that would set your delta x, delta y. Okay? But in a problem like this, then you're asked to figure it out based on what the frequencies are in the object. All right? So any questions? Okay. So, and just sort of as a teaser, notice that from this period, I could have directly gone to here. And from this period, I could have directly gone to there. Right? That's the highest. If that's the highest frequency, the frequency of that cosine is 3. So I know my kx max should just be 3. And the period of that other cosine is 2. So in ky, it's just 2. So that's the other way you could think about it. And sometimes it's actually very useful to think about lots of ways of looking at problems, both for courses and also for research. All right, any questions before we talk about the final project? Okay, so let me turn this down. I'm going to stop this.